All right. And that's good. Yeah, did somebody have a question? Go ahead, Samantha.
Yes, quick question. The labs don't meet until next week, right?
I'm sorry, say that again.
The labs don't meet until next week, right?
No, they're gonna, so hopefully they'll meet this week. So the labs are really recitations. I don't know why that's a mistake on in ASAP. I don't know why it says labs, but that's what it says, but they're recitations. So you're gonna go over homework problems in the recitation. And I gave the book people the homework problems to add to it as an appendix. I don't know, a couple weeks ago, but I don't see it. Let's see, let me look real quick and see. I don't think it's, no, they haven't added it yet. So I'm going to ask, I'll ask the book people about that today. In fact, maybe I'll send them an email right this second.
Does that mean we can maybe have a little bit more time for the homework?
Yeah, so the first, yes, we'll have to have a little bit of a flexible schedule. So what I'll do, I'll probably put the file on Blackboard. I don't know. Anyway, we'll figure it out. But let me send this right now.
Sir?
Yeah.
I was going over the syllabus to organize like everything that has to be done throughout the semester. And in the syllabus, a lot of the dates said things were due in October, November. So I wasn't sure if like it was the syllabus finalized or anything like that.
Okay, so I had trouble understanding everything you said, but something like in the syllabus, there was a date about the 4th of November or something. Is that what you said?
Yeah, a lot of the due dates for like the projects and any of those type of assignments late in the semester.
Okay, so let me see, because I don't see that. So here's the syllabus. So let me share this. I'll send that email to Tracy in a minute.
I think he's talking about just like all the other stuff that's on the Blackboard page.
Yeah,
the syllabus doesn't have that stuff.
There probably are some things that I haven't hidden that should be, but the syllabus, I think all the dates in the syllabus are exactly correct. So if you go by the syllabus, you'll be fine.
Well, by around week 9 is when it's for the syllabus that I downloaded from Blackboard. I checked again and it kept on saying around week 9 and so on. It kept on saying that it was the due dates were like due in October or November.
Well, okay, so let me look. So this is the syllabus here. So week which? So that's
week 9.
So week 9, March 7th to 11th. Homework due March 11th, March 11th, March 11th. So I know that's all correct. So let me see what maybe the one on Blackboard isn't updated. That's possible, I guess. So let me look. Course. Let's see. Here we go. So you're saying week 9, huh? Oh, yeah, I guess these, yeah, these 2 end of chapter quizzes were, I wonder if is that true on mine as well? Didn't see that, but maybe it was. There's only about 500 dates to change. But maybe that's right. Yeah, okay, so in the entire frickin' syllabus, there are a couple dates here that are October. You're right. I will fix that. By the way, it's not week 9 yet, so don't worry. But I'll fix that. That's a mistake. But if you go to the end of the syllabus right here, this lists all the dates open and close time, and they're right. So just ignore the mistake. Okay, and go off this list at the very end of the syllabus. See this list here? That's the definitive correct list. I just missed copying the ones for week 9 here. So it should be March 4th and March 22nd and March 21st and March 23rd. So Yeah, I'll try and do that. I may forget to do that actually, but
Yeah, I was just organizing myself, and then I saw about the teams and when the assignments are due.
yeah, I
and
understand.
I was
And
confused.
it's good. And I'm glad you're doing that. You're organizing yourself. But this is the list. I know this list is all correct. And that's what's uploaded to the book. So yeah, I missed that. But yeah. And there's another one here too. So it looks like some of the, it looks like I missed some of the end of quiz dates. Yeah, I don't know. You wouldn't believe how long it takes. I spent hours and hours updating this syllabus for this semester. And I did miss a few things, so I'll try and fix that. All right. So anyway, getting back to where we actually are. Down here. So week 2. So we're on January 24th, and we're going to talk about number systems and simple binary math. And so we'll talk about chapter 2 a little bit. What I want to do right now is just go over the number systems and how we generate, how we switch from one base to another and some things like that. So I'm going to go through that. And so let's see. Oh yeah, sorry, you can't see that. Let me share the screen. So if you go to the very end of the syllabus, if you scroll all the way down, there's a table down here. So summary table of quiz availability and closeout dates. So that's correct. Okay. But there are a few, and I saw like yeah, and there may be a couple. Yeah, I'll try and go over and make sure. There were a few places where I didn't get it updated for some reason. Okay, all right. So I want to talk about. Let's see. So yeah, this is okay. And yeah, that's really interesting. Okay, so let me pull this up and we'll jump into it. Okay, and it's coming up. Yeah, no, that is not actually. Okay, so let me go back to things. Okay, yeah. So let me go through this, and okay, I'm going to see. You're already seeing the screen. Okay, can everybody see that slide? All right, so we're going to talk about base 2 number systems, and these are. I think I said it the other day. Just it's really amazing. It's surprising that we don't get this covered. You know, in kind of the grade school or for sure middle school, and absolutely should be, you know, just standard fare in high school. But it doesn't get done because it confuses. It's a little bit confusing to some of the teachers, and so it's kind of been pushed out of the way. But all number systems work the same way, and are all the bases work the same way. And so let me bring up my little projector here, and we'll do that because I want to actually draw some things. And I'm gonna. So let me see if I can. Let's see. So, all right. So I'm going to bring this up here. Hopefully, yeah, there we go. For some reason, it's super laggy. I'm not sure why. All right, so when we write a number like 256.35 or something like that. Let's see, let me focus it. So when we write a number like that, what we're really saying, and this, of course, we're in the decimal world, we always assume base 10. All right, good. All right. No, I leave it there, please. Okay, so we write a number like this. So we're assuming base 10. So sometimes we'll write a little subscript like that. Sometimes we won't. And but what we're really saying is that we start with the decimal point. And when we go to the left of the decimal point, we start with the base to the power of 0, and we increase by 1 each digit. All right, when we go to the left of the decimal point, we take the base to the power of -1, and we decrease by 1 each digit. So what this really is saying is, it is 6 times 10 to the 0 power plus 5 times 10 to the first plus 2 times 10 to the second plus 3 times 10 to the -1 plus 5 times 10 to the -2. And you add all that up and you get 256.35. That's how that number works. That's what that means, and that's how it works. And it's the same for all bases. So when we write something in base 2, it's the same thing. Now, we consider 10 to the 0 power. This is considered a positive number. Well, of course, 10 to the 0 equals 1. And there's actually a great little video that shows you how this any number to the 0 power, how that's worked out. And it's actually kind of crazy. It's as you approach 0, you get that result, but it's a result in the limit, and it's actually a mathematical curiosity. If you're interested, you can pull up that YouTube video. It's kind of an interesting video to look at. You realize how so much of what we just take for granted and assume is actually rather complicated. Anyway, so that's how we put together this number. So if we do, for instance, if we do something in base 2, so for instance, we do say 110110.11. So that actually represents 0 times 2 to the 0 plus 1 times 2 to the 1 plus 1 times 2 to the 2 plus 0 times 2 to the 3 plus 1 times 2 to the 4 plus 1 times 2 to the 5th plus 1 times 2 to the -1 plus 1 times 2 to the -2. And if you add all that up, that's what that equals. Now, with powers of 2, it's pretty easy because you should know those, pretty much off the top of your head. Now, first off, when you do this calculation, you're doing this calculation in decimal. Whenever you do math in your head, you're doing it in decimal. You don't do math in other bases because you've never learned how to do that. So you only can do math in for the most part, at least, in decimal. Even when you look at a binary number and do math on it, you probably are switching it to decimal and then doing the math. But certainly this expression here that I just wrote out, that's decimal math. So this is a base 2 number, but this is all decimal math because I have 5s and 3s and 4s and stuff, which aren't legal. In any given base, we have the base. So we have the, let me get another piece of paper here. So we have the base, which in the case of decimal is 2, in the case of 10, in the case of binary, it's 2. In the case of hex, it's 16. And those are only the bases we really use. Anything else we never use. Just doesn't exist really. I mean, it exists, but we never use it. All right. So we have the base, and then we have the symbols. So what are the symbols? Well,
Like
in decimal,
zero.
go ahead.
Right, yeah, decimal would be like 0, 1, 2, 3 through 9.
That's right. 0 through 9. So what is it for binary? So this is decimal. What are the symbols?
Just 0 and 1.
That's right. And what about hex?
0 through 9, then A through F.
That's right. Now here's the tricky thing about this. I think they really abrogated a responsibility here when it was obvious that hex was going to be important. They should have created new symbols, because what do you see as a potential problem with A through F?
We don't know if those are just words or these are original numbers.
That's right. If I write BAD, is that a hex number? Is that a word? But that's only one problem. An actual bigger problem is, what about uppercase and lowercase? There are two actual different symbols for A. There's A and there's A. And there's F and there's F. Which is it? Those have different, remember we talked about ASCII last week? These have different ASCII representations. So when you see these in a computer, this A is not the same as A, totally different. And if you ask if they are equal, they wouldn't be. So when you compare numbers, at least in using ASCII symbols, you don't know which one of these, they aren't equivalent. And so now you have to make special rules and exceptions to account for the uppercase and lowercase letters, A through F, which is really a pain in the butt. And it's really kind of sad that they didn't just go ahead and create some new symbols. In fact, maybe you should create your own symbols and we'll submit them to the group that manages some of the character sets, and see if somebody wants to get excited about new symbols, because it really would be nice to have unique symbols for the symbols that represent 10, 11, 12, 13, 14, and 15. So A represents 10, F represents 15, and everything in between. Go ahead. Question? All right. So anyway, so we do have symbols for hex, but we appropriated some new, we dual purposed some other symbols and added them to the symbol set for hex, which in my view is, has caused some confusion. But that's what we're stuck with. Okay. So the other thing, so now how do we get from one base to another? And it's kind of interesting. So it depends on whether you're dealing with the integer portion or the fractional portion. And then what are some of the special exceptions? Well, we'll talk about the special exceptions in a minute, but there is a special exception for base 2, obviously base 4, base 8, and base 16. Those all have special relationships. And that's because one base 4 digit, which we don't ever use, is exactly 2 binary digits. And one base 8 or octal digit is exactly 3 binary digits. And one hex digit is exactly 4 binary digits. And so because we deal with 32-bit words and 64-bit words, it is really awkward to write out 32 ones and zeros. You're guaranteed to make mistakes, lose your place, have trouble with it. And so we what we do instead then is we we translate these directly into hex, and we always represent a 32-bit and a 64-bit number in hex digits. Now, as our bit widths get greater and greater, now pretty much standard 64. If we get to 128, that begins to get very tedious in hex. So we may well go to some other base one of these days. You'll see people introducing base 32 or maybe even base 64. So that's going to be interesting to see how if that develops. But we are dealing with bigger word lengths. So how many hex digits does it take to represent a 32-bit number, a 32-bit binary number?
8.
That's right. It takes 8 hex digits. And so that's not too bad. But now for a 64-bit, you've got 16 hex digits. That's a lot of digits. And so you can see how there might be a push down the road coming to pick another base. So who knows what that might be. But I suppose 32 is the most likely. All right. So let's look at how you would convert a binary number into a hex digit. So if you have, so what you do, let's say we have a number like this, 011101101110101, say. All right. So first off, if you have leading zeros, you can always add leading zeros or take them away. And if you have any trailing zeros, you can add them or take them away. It doesn't change the value of the number. So the first thing you do, you start at the decimal point and you divide the number into groups of 4 binary digits. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2. Okay, we'd only have 2, so we can pad it out to zeros if you want to have a complete 4 there. And then here, do the same to the right of the decimal point. 1, 2, 3, 4. 1, 2, pad out to 0. Now on this side, padding out's not super critical, but here it is critical to pad it out so it makes sense to you. Otherwise, you'll come up with the wrong digit. All right, now we take each group of 4 and we directly translate it into its hex digit. Now, I don't ask you to memorize much, but I'm going to ask you to memorize this, and you should do it today. Just sit down tonight and work this out and just memorize it. It's easy to calculate in your head if you forget, and there's some that I have a little trouble with. But if you memorize most of the digits, then you can figure the ones that you don't know. And you should just do this little exercise like this, where you write a little column 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Well, we'll say A, B, 12, C, 13, D, 14, E, and 15, F. And then you write out to the side its binary equivalent in 4 bits. So this is, of course, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, and 1, 1, 1, 1. You should know those by heart. That will help you in everything you do in the digital world for the rest of your life. And since you use them so often and so frequently, you just need to have them memorized. It's not that difficult. That's one of the only things I'm going to ask you to memorize. So, but do that, and that'll really help you throughout this course, your next course. It'll help you your whole career. So just memorize those, just like the multiplication facts you have to do, which of course are all decimal facts. And it's probably good, instead of writing, you probably should switch when you want to write 15. You should probably use hex, for the first 16 numbers. The other thing in the digital world, remember, we always, except when we don't, start with 0. So when we count, our first count's always 0. This causes no end of confusion because up till now you've been taught to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But the correct count in the numerical world is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's just how it is. So so just always remember, we start with 0, except when we don't. And unfortunately, there are cases when we don't. But most things we always start with 0. So it's interesting. On outputs, a lot of times we'll start with 1. And then say we have 5 outputs or 6 outputs or 8 outputs, they'll be labeled 1, 2, 3, 4, 5, 6, 7, 8. Although actually, if they're 8 outputs, we might label those 0 through 7. But if we have address lines, we're always going to start with 0 on address lines. So don't ask me why. It's a little screwed up like that. But for most things, we start with 0. So just keep that in mind, except when we don't. You know, in the C language, when you define, like if you define an array, you know, let's say we define an array of ints array, and we do say 16. You know that the legal values for array will be array 0 through array 15. 16 will be an illegal value because we start with 0. And that's true in most things. But there are, and when you take an integrated circuit and it has pins on it, well, the first pin is pin 1, not pin 0 for some reason. There's no pin 0. But if there are address lines on this chip, they will be A0, A1, A2, A3. So there are some goofy things like that, but just remember, we always start with 0, except when we don't. That's maybe the only way to say it. All right, so back to this. So we're going to take these groups. We're going to take these groups of 4 in our binary number, and each group of 4 directly translates into one of the binary digits using this table right here that you're going to memorize. And that allows you to instantly translate this number. So I can look at this. So now the hex number that's equivalent is going to be 1. This is going to be, so 1100C. So 1101 is D. So 1D, 7. And then this is another D, and that's 4. So it's 1D7 decimal. Now, the idea of calling this a decimal point, it's not really a decimal point when you're writing a base 16 number, is it? Because it's only a decimal point in base 10. So we usually call this the point. We don't call it the decimal point anymore. And that's why, sometimes we'll call it dot. That's why you see, you know, in the internet nomenclature, it's, you know, it's something.com. We don't call it the decimal point or the period. All right. So let me switch back to the slides. So this base 2 number system has a special relation to octal and to hex. And then we're going to talk a little bit of how you convert from base 10 to, say, binary or vice versa. All right. So base 10 is our standard system. So 953.78 base 10 really equals 9 times 10 to the second, 5 times 10 to the first, 3 times 10 to the 0, 7 times 10 to the minus 1, and 8 times 10 to the minus 2. There are other bases, and like we said, hex is a good one. And this is just, so A32 is just 10 times 16 squared, 3 times 16 to the first, 2 times 16 to the 0. And then octal, we don't use octal anymore. It used to be very common in the computer world and digital world. Almost all my early programming, I had to use octal. But it went away when our instructions got a little larger. We used to have 12-bit instructions were very common, and that divided nicely up into 4 groups of 3. So 4 octal digits would describe the instruction, and that's why we used it. But now our instructions are a lot bigger, so we just use hex, and we don't use octal anymore. All right. And then we talked about this already. We pretty much represent the internal binary numbers with hex just for sake of convenience, so we don't have to have 32 ones and zeros. And these are the ones you know, A is 10, B is 11, C is 12, so forth. You should know this in your head, and you should go ahead and memorize that little table I showed you. All right. And here's the little table. So just you know, get this down, commit it to memory. I'll have to admit, I know, of course, 1 through 9 are easy. You kind of know those because they're mostly just 3 bits, except for 8 and 9. And 8's just that, and 9 is 1001, which is kind of easy. A, I remember A is 1010. So that's kind of easy. A is 10, and 1010 is the hex equivalent. So that's how I know A. And then, of course, I know B is just one more. And for some reason, it sticks in my mind pretty well that C is 1100. And obviously, you know, F is all ones and E is missing the last one. So then the only one that's a little confusing, I sometimes have to think a little bit to come up with D. That's the one that tends to, I find confusing. So if you just memorize make a little trick for yourself for D, and you won't have my handicap. But anyway, that's how that works. All right. So we talked about converting from binary to octal. You just divide it up into groups of 3, but from hex we do groups of 4. All right. What about negative numbers? This is a very, very interesting topic, and this drives a tremendous amount of the computer world. So it's super important, and it's super important for you to understand this really well. I don't know. It's a little off-putting at first, but once you kind of glomp onto it, it starts to make a lot of sense. And there are good, solid reasons for why these things evolved. So they're basically maybe 3 different ways you could represent binary numbers as positive numbers and negative numbers with a fairly simple system. The first that you might think of is called sign and magnitude, where you identify one of the symbols, one of the digits is it represents whether the number is positive or negative. And it turns out we use this for floating point numbers. When we use the IEEE 753 standard, this is exactly what we do. And there's kind of a reason for that. But for all of our integer numbers, we don't use sign and magnitude. We use 2's complement. Now, the other way you could do it is 1's complement. So what's the difference between 2's complement and 1's complement? Well, I'll explain that. Let me go back to the drawing. Let's see, where is it? So let me get another piece of paper. All right, so if we, so let's do we'll take a little binary number. So we'll do a simple one. Let's take 5, okay? 0, 1, 0, 1 in four digits. So that would also be, so that's hex 5, it's decimal 5, and it's binary 0, 1, 0, 1. All right. So it's 5 in octal too, actually, for whatever it's worth. Okay, so let's say we're going to take the complement of this. Well, so when you take a complement, the first question you have to ask is, will the number of digits be enough? So it turns out that we call our 2's complement numbers, signed numbers, and we call our non-signed numbers, we call them unsigned. Makes sense, I guess. So in the C language, when we declare an integer, we'll declare an integer, say, we'll call it A. It depends, it's language, it's a compiler specific, how many bits we set aside for this. It could be 32 bits, it could be 16, it could be some funny number. That's not specified in the C language standard. But it depends on the compiler, and that of course typically depends on the target hardware. in most microprocessor languages, the compiler specific size of this would be 16 bits, but it could be 32. There are certainly ones out there that are 32. So if you have 16 bits, 16 binary bits, what's the biggest unsigned integer you can represent in 16 bits? Maybe we should do it with 8. Just forget this. Let's just say in this weird compiler, the compiler specific definition actually is, well, let's change this to a char. So now that's 8 bits. So what's the biggest number you can represent unsigned in 8 bits? Somebody tell me.
Is it 511?
That's actually 9 bits. But 8 bits.
Oh, so 255?
It's 255. That's right. Exactly correct. So it's 255. Now, so if I have, so it turns out if I do signed numbers, I only get half that range, right? Because I got positive and negative numbers. And in fact, I have 128 positive numbers, and I have 128 negative numbers. Now, this is also a little confusing. What number do my positive numbers start with?
One.
Remember this rule?
0.
That's right. They start with 0. So if we have 128 positive numbers and they start with 0, what's the biggest positive number?
127.
That's right. The biggest number is 127. Now, what are my negative number? What's my first negative number?
0?
Nope, because 0 is a positive number.
-1.
That is correct. So if -1 is my first negative number, what is my biggest negative number?
-127.
Nope, because when you count starting with 128 numbers, the number you get to would be -128. So if I start at -1 and I go to -128, that equals 128 numbers. And if I start with 0 and go to 127, that equals 128 numbers. And when I add those together, that's my 256 numbers, which is 0 to 255. And in here lies all the confusion that exists in the world of binary numbers. Because you have to remember that in 8 bits, you don't get 256, you get 256 different numbers, but they're numbered 0 to 255. So your biggest number is 255. But in 2's complement, you only get half that, and you get cheated out of one of those on the positive side because you start with 0. So you get 0 to 127, 128 positive numbers, -1 to -128, 128 negative numbers. But the biggest positive number is 127, but the biggest negative number is -128, or the smallest negative numbers -128. All right, so you can see why that's a little confusing. It's only confusing at the margin, right? At the limits. Within the limits, it's pretty straightforward. But one of the problems when you want to change a number from a if you want to take a 2's complement, the first thing is you have to make sure it will fit in the number of digits you set aside. So for instance, given that we have 8 digits and we're doing a binary number, okay, obviously, can I represent minus 140?
No.
That's right. I can't do that because it's bigger or it's smaller than -128. Can I represent positive 128?
No.
I can't do that either. My biggest number I can do is 127, positive. Can I do minus 128?
Yes.
I can. But the amazing thing is, I can't, if I try and take 2's complement and 8 bits of minus 128, what do you think I get? I can't get plus 128, which is what you'd expect, because it doesn't exist in 8 bits. It turns out I get minus 128 again. Crazy. So you have to be careful that the number you're going to screw around with will fit in the size you've specified, you've allowed. Now, you know, in a perfect world, you can have an unlimited number of bits, but in the real world, there are constraints on everything we do, and we don't have unlimited number of bits. All our computers have finite memory in them. So it really helps you. It really helps you to be able to have a mental picture of what can fit in what. And here's where this gets you into trouble. Let's say you're writing a C language program and you're going to do a for loop. So up here you do int j, and then down here you do a for loop for j equals 0, j less than 40,000, j plus plus. And then you're going to do some stuff.
Can you move the paper up?
What's that?
We can't see what you're writing.
Oh, sorry, it's off the page. Yeah, I should have flipped it. All right, so I define int j, and then I write this for loop down here. Is this good? Let's say my compiler specific, I have 16-bit integers. So first off, when I write this, what is j? Is it a signed or an unsigned number? In other words, is it a 2's complement, or is it just an integer with a magnitude? No plus or minus. Unsigned.
Integer with the magnitude?
No, it's a signed number. By default, they're signed. Unless you specify it, it's signed. So if you want it to be unsigned, you have to append it. You have to add that. So if you don't add that, it's signed. Now it's better to use the new nomenclature, which isn't official, but where we would specify whether it's assigned and unsigned and that sort of thing. So for an unsigned, we call it a uint space t 16. So that would be our underscore t16. That would tell us that it's a 16-bit unsigned integer. But and you don't allow this construct because it's confusing, because unless you remember what the default is, you're confused. All right. So now what about this comparison? Do you see a problem with that comparison when j is unsigned? I mean, when j is signed. So what's the biggest integer that you can have in 16 bits, say unsigned? Well, so it'd be 2 to the 16 minus 1 minus 1. So that's 65k minus 1. But what's the biggest integer you can have if it's signed? Yeah, actually not 64k. The biggest if it's signed is 32k minus 1. And what is 32k? I guess I should do that. I don't remember. Let me get calc. So if we do, let's see, I'm gonna do, let's do 2 We have to do scientific.
It's 32,768.
So 32,768.
Yep.
Yeah. Okay. So that's the biggest, and minus one. So it's actually 32,767. That's the biggest positive number I can have the way I defined J. So now if I look at this, what about what's going to happen when J gets to what was it? 32,767 plus one. What is that actually going to be in this, for the purpose of this comparison? It's going to be minus one. Is minus one less than 40,000? Yeah.
Yeah.
So it's never going to be, this is never going to be correct. This is never going to execute. It's always going to be true, no matter what J is, because J can never get that big. So it's not going to work correctly. You might even have the, yeah, I mean, it's going to get stuck there. So what's going to happen? So you see why this is important. Turns out these issues of signed, unsigned, and how they're done actually is really important. Okay, so let me shrink that down. Okay, all righty. Maybe. Okay, so when you do a two's complement, then the first thing you have to do is make sure you know whether the number you're taking the two's complement of will actually fit in the number of bits you set aside. Because now what you're doing is you're taking a signed, an unsigned number, and you're turning it into a signed number, which is fine, but you just have to make sure it will fit. And if it doesn't fit, it's gonna give you fits. So you need to make sure you get this right. Okay. So how do you do the two's complement? And why do we do two's complement and not one's complement, or sign and magnitude? Because those are the other ways we could represent negative numbers, other simple logical ways. And I guess there's an infinite number of ways, but those are the three that make some sense. But of the three, two's complement is the one we use. And the reason we use it is because it makes the most sense. Again, with the exception of floating point numbers, where we do use sign and magnitude in the IEEE 753 standard. All right, well, so one's complement. Let me go back to the sheet one more time here. And then we'll finish up here soon. So I'll pull this back up. Okay, so sign and magnitude would be, let's say we have 8 bits again. So let's see, so our first bit here would be a sign bit. One would be, and it turns out 1 is negative and 0 is positive for some reason. All right. And so then 1, and then 1 1 1 0 1 0 1, something like that. All right, so there's our binary number, and we'll let this be the sign bit, and those will be the rest of the number. So we'll have 7 actual bits of the number and then a sign bit. Now, tell me what is, so this would be, what's the value of this number here?
Is that -1?
No, this would actually be 0.
Oh, that one, sorry.
Wasn't really a trick question. Yeah, it's just 0. What about this? So that would be positive 0, right? Because remember, 0 is positive, 1's negative. That's our sign bit. What about this number over here?
-0.
Yeah, what do you think, Joshua? Could that maybe confuse our little computer brain?
Yeah, that's kind of weird that it can be simultaneously both.
That's right. It's not just a little weird, it's a hell of a big problem, because now you have to write special software to recognize that, because no other 2 numbers are equal except these 2. So that's a little confusing, and that's a problem. So with sign and magnitude, so we have the sign bit and then the magnitude, we have two values for 0. All right, so that's one problem. There's another problem too, and it turns out that the hardware to switch between addition and subtraction is complicated when you use sign and magnitude. All right, so complicates hardware. And then so two values for 0, that's confusing. Complicates the hardware, that's also confusing and problem. Well, that's a problem. All right, what about ones complement? So so how do we do ones complement? Ones complement is we take every bit and we flip it. So for instance, if our value is up here, so this was 11110101. So that would be hex F5. Okay. Now we flip it. So that's 00001010. And that's hex now. That's hex 0 A. Okay, fine. So what's the problem here? Well, it turns out so let's say we have so let's say we have 0. Okay. So this equals 0. What is the ones complement of that? It's just FF, right? In hex. So now we have two wildly distinct values for 0 because this still well, it turns out that these are both values for 0. Because when we complement this is what we get. We don't, it doesn't work. All right. So in ones complement, we have two values for 0. Because when you complement 0, you really need to get 0. And when we complement 0 here, we get FF, which also means 0. So that's a problem because now we still have two values for 0. But in 2's complement, what we do is we take every bit and we switch it. So we switch every bit. And then we add 1. And that gives us the 2's complement. So it's just like 1's complement, only we add 1. Now, one more rule, which normally isn't stated, is we ignore overflows. Or actually, I should say carry outs. So what happens when you add 1 to FF? What do you get if you ignore the overflow?
Can you move the paper up, sir?
Yeah, I think, yeah. So let's do it. We'll take it in, we'll do it in 8 bits. I mean, in 4 bits, say 1, 2, 3, 4. All right, there's 0. Now we'll do the 2's complement of 0. So first we flip every bit. Now we add 1 and we ignore overflows. What do we get?
You'd have to add a 5th bit.
Yeah, but we're going to ignore overflows.
Oh,
When it just becomes zeros here.
We get zeros. Perfect. Exactly what we wanted. The complement of 0 is 0. Not true in sign magnitude, not true in 1's complement. Only true in 2's complement. In 2's complement, there's only one value for 0. And that's why we use it. Doesn't confuse our hardware, and everything works great. The only little confusion the hardware has to endure is there's an overflow, the 5th bit. But we just tell the hardware to ignore it, and everything's fine. It turns out in unsigned addition and subtraction, the carry bit's quite important. We have to keep that in mind because that tells us we overflowed. But in two's complement, we don't pay any attention to the carry bit when we do two's complement math. We have another method for determining overflows, and we'll talk about that later because we're out of time today. All right, so hopefully this gets you started, and then we'll finish up with this, and we'll move on to chapter 3 on Wednesday. Any questions?
Excuse me, Professor, when you did the for loop example,
Yeah.
how come when that character tried to approach 32, it reset down to -1? Is that like what happens with overflow?
No, that isn't overflow. Yeah. So what happens? Yeah. So the value. So yeah. So if you think about it, so what would so in 16 bits. So what happened? We got 1 1 1 1 1 1 1 1. So this would be that's 8 bits. But if so it's easier to do in 8 bits because the numbers are too big in 32K. But think of it in 8 bits. So when we get to this, that's positive 127.
Excuse me, sir, could you share the
Oh, sorry. I'm sorry. I forgot. Yeah, I do. Yeah.
Thank you, sir.
All right. So in 8 bits, we count up here and we're at positive 127. What happens when we add one more to this? And remember, the computer considers this signed. So the first digit basically tells us it's not a signed bit. It's part of the number, but it does tell us whether it's negative or positive. So if it's a 0, it's positive, but if it's a 1, it's negative. So now add 1 to this, what do you get? Now, what does that equal? What does that equal in 2's complement? It's probably hard for you to guess because unless you just happen to, but that is minus 128. So you see the number jumps from positive 127 to the largest negative number we can represent, which is minus 128. And that screws up your compare. Remember, your compare is j less than, in this case, it was, let's say it was, say 200 here. Well, it's always going to be less than 200. It's never going to be over 200 because it's a signed number. So the maximum value it can have is plus 127. And this value, the computer considers minus 128 because it's signed. So when you declare it, you had to say unsigned. Now, if you did that, you're okay. Now you're good. In 16 bits, you're good to 64,000, whatever it is. So the 40,000 would be fine. But if you didn't specify unsigned, by default, it is signed, and then it doesn't work. Are you tracking now?
Yes, sir, I understand. I appreciate it.
Sure. No, and that's an important point. How many freshman computer science students do you think make a mistake with that?
All of them.
Probably all of them. Yeah, it's a subtle error. Okay, one of the reasons why there's a push to go to the I forget what I don't know what the official name is, but the more precise specifications of integers and characters, and I think it's very, very helpful, and especially for microprocessors where in a with a microcomputer and a mainframe or whatever, you're not so worried about the size of your integers and your variables. But in a microprocessor, in micro 1, we use the PIC 16F1829, and it's got 1K of random access memory. That's it. So if you create an array of, a large array of integers versus chars, it doubles the size. And it could easily exceed the capacity of your memory. So you do have to pay a lot of attention to the size of your integers. And sometimes you want to use, and that's why the IEEE 754 standard on floating points changed about a year ago, and they created several new categories to give you more flexibility in creating floating point values. All right. Anyway, we'll talk more about this. There are a lot of things about about positive and negative numbers, floating point numbers that are really important to know for digital design purposes. All right, we'll pick this back up on Wednesday. Any other questions?
Sir, I have a question really quickly. When you were talking about the binary, you were talking about padding the zeros to the right. Can you explain that to me? Because if you were to do that, that would essentially change the number,
No.
would it not?
You have to the right of the decimal point.
To the right of the decimal. So if it's a decimal number, you would pad it with zeros?
Well, no, so remember, a binary number is not a decimal number, but it has a point as well. So like 1101.1101, okay? So you can pad out here all day long and you can pad out here all day long. But obviously, if you
I can't
pad,
see what you're doing, but so
Yeah.
only in the case when there's a point involved is when you would pad it to the right.
yeah, so
Okay.
here a number like this. So you can put zeros here, it doesn't matter. What you can't do is insert zeros between the least significant digit and the decimal and the point, the binary point or the octal point or whatever.
So if there was a point involved, would that change the direction in which your count goes? So instead it would go 1, 2, 4, like -1, starting at that one after the point?
It's always at this point where you go in this direction, you're always doing 0, 1, 2, 3 powers of your base. This way you're always doing -1, -2, -3 powers of the base.
Okay, that makes so much sense. I appreciate it. I'm a former signals analyst and we did binary, but we never had decimals. So when you started talking about padding to the right, it confused me to high heaven and I had no idea what you're talking about.
Yeah, got it. No, that's okay. No, that's good. It's a good background to have. Yeah, no, it's only true. Obviously, if we could add zeros willy-nilly, I'd just add some zeros to my salary. That'd be great.
Yes,
But
do it.
if I add them on the after the 1 cent column, it doesn't really help me, does it? All right. Very good. Any other questions? Last chance.
Sir, I had a question, but on the homework for this class, I was still confused as to how or where to access it.
Okay, so that's going to be done in recitation, and I haven't met with the TA yet, and so they don't know what to do, and they're clueless. And so because we're virtual, I'm going to try and meet with them all on Thursday this week, go into UTSA and hopefully meet with them and get them kind of plugged in. So I guess we're probably not going to have any recitation sections this week either. So hopefully we'll crank everything up next week. It's just logistically difficult when they don't, yeah, it's just a problem. It takes a little bit. And even though some of them, I just found out who the TA was for this course over the weekend. So there's just no way to get it set up early, but that's just how it works out. But so no recitation this week, which means we're going to be a couple weeks behind the homework. Don't worry about it. We'll probably just start with week 3 homework. I don't know. Don't worry about it. Well, so I did talk about this briefly. I'll cover it again. I'll kind of review things on the homework again on Wednesday. So for now, don't worry about the homework. The only thing you have to worry about are the end of chapter quizzes. And
Thank you, sir.
Use that table at the end of, I'll fix the mistakes on some of the later weeks. I know the first weeks are correct, but there are some funny dates in the later weeks. I'll fix those. Yeah. All right. We will see you guys later.